看一下。好，好了。可以，应该是可以的。
你没有跟他们讲什么？
没有人啊。要看老师是吧？
这个是什么？
有。
Okay, so let's start. So I thought it's better for me to derive this equation for you. So last time we defined the so-called wave impedance. So wave impedance is basically the total. So the wave impedance, ZD, or Z as a function of distance along the transmission line, including the load impedance, is the total voltage as a function of space divided by the total current as a function of space. So this is J beta D plus gamma B exponential negative J beta D. And then the total current divided by Z0, but the same thing, but having a minus sign. If you still remember, the reverse current is having a negative sign. All right. So the forward voltage amplitude cancels out. So now we have this expression. Okay? We're looking for an impedance. So indeed, the voltage is canceled out. So now the characteristic impedance is now in the denominator. Okay? And then it's multiplied by some kind of complex value. So in order to derive the equation marked by the yellow on the PowerPoint, we only need to insert the expression for voltage reflection coefficient, gamma V. Okay. If you still remember, gamma V is nothing more than Z load minus 1, Z load plus 1. So here, the load impedance is normalized by the characteristic impedance. Okay? So we only have to replace gamma V by this expression. Okay, so let's do the procedure. So after I finish all the derivation, the teaching assistant will take a picture for you. And at the same time, our Center for Teaching and Learning Development is working very hard. So they are trying to ensure all the classes will be edited within the week, right? So if you have trouble jotting down the notes, we have photo, and we will have a very clear edited version of video by the end of this week. Okay, so I need to thank all the staffs here. So at this time, all I have to do is normalize, right? I can multiply everything by this normalized low impedance plus 1. So that is minus. Remember, here you have a minus. Okay, so now let's collect terms. The terms having the normalized low impedance and the ones not having the low impedance. So Z load normalized will have J beta D and minus negative J beta D and plus exponential J beta D plus, right, plus, okay, and minus exponential negative J beta. On the denominator, I have Z load and now I have minus. And now I have plus. And then plus. Okay, so when we look at exponential J term, plus its complex conjugate, I have 2 times the real part. The reason is exponential J beta, it's called Euler's identity, is cosine beta plus J sine beta, right? This is something we learned from maybe high school. You're all smart, so your high school level is very high. Okay. Right, so the top part, this is becoming 2 times the real part. The real part is cosine beta D. And this one, this minus is complex conjugate, so now you have 2 times the imaginary part. So 2 times J imaginary sine beta. Right. All right, so at this moment, all we have to do is divide the top, the numerator, and denominator by cosine beta D, so we can have tangent. Right, so in the end, this is Z0 normalized load plus, and then we can divide by 2, right? 2 cancels out. By J tangent beta D, and then it's the real part, 1 plus J Z load normalized tangent theta E. Okay, let's compare to what I wrote down in the PowerPoint for you. Hopefully I didn't make any mistake. Okay, reads the same. So this is really nothing new. It's something you want to do live. You want to spend maybe 10 minutes. And then in the future and afterwards, you can simply use this formula so you can quickly understand what is the effective impedance, right? We started from the load, right? We understood the reflection coefficient, and then we walk back to our input, and then we look into the entire transmission line plus the load. And then we can use this simplified notation to express the entire transmission line, including the load, as an effective wave impedance. Okay? So remember, the wave impedance will definitely be a function of distance. But the characteristic impedance, Z0, is a constant, which is defined by your transmission line. Okay? So you have to pay special attention to being able to differentiate the two. Characteristic impedance is a constant. It's provided by the transmission line. But the wave impedance is the total voltage as a function of space divided by the total current as a function of space. So it will be position dependent. It is a function of D. Okay? All right, so I went over this slide quite quickly last Wednesday, so I want to spend some more time on this, right? So now we have formally derived the expression for the wave impedance. As I said, our knowledge to the transmission line gradually increased. We know that on the transmission line with some kind of load, we have forward propagating wave and backward propagating waves. So we have two waves. And once we have the two waves, it will create some kind of standing wave, which we explained on Wednesday as well. Okay? So now, we want to solve for everything. So the idea is we know the reflection coefficient, so we know how strong the backward propagating wave is at this point, at where the transmission line is connected to the load, right? And then the strategy is we walk back until we meet the input point. And then we look to the right. And then we say, this is effectively a load. And that load can be defined as my input impedance, right? The effective impedance that I see when I stand at the input point and look into the right. And look into the right means including everything. So now I have the power to write down the transmission line, including my load, as a single effective impedance. Once I can do that, I can write down my input voltage. That's something we learned for voltage division rule, right? So we know our input source voltage is VG, and I have my intrinsic generator impedance, and now I have my entire effective input impedance. So the power distributed over this input impedance is VG times voltage division is VZ, sorry. ZG plus ZIN and then it's proportional to how strong or how big the impedance is, right? So this is my VIN. But this VIN, at the same time, I already know my expression for the total voltage everywhere on the transmission. So that is V total at L, right? What is L? L is my total of my transmission. So this is equal to V0 plus. Finally, this is the only last parameter we want to solve, right? V0 plus. So somehow I can relate this unknown variable, the very last unknown, to everything I already know. So let's check. This is given, right? I have to know my generator voltage phasor, and ZIN, known. Generator intrinsic impedance, known. This is known. I know my length. I know my transmission line. Knowing my transmission line means I know beta, right? I know the effective wavelength. I know beta. And I know my load. Once I know my load impedance, I know my reflection coefficient. So the only thing I know here can finally be solved. Okay, so let's come back to the PowerPoint. So this is again, just to repeat what I wrote on the blackboard. Okay, so this, my input voltage is determined through the voltage division. Okay, and then that voltage is my total voltage phasor at the distance of L, equals to that. So finally, we have the proper mathematical formulation for the forward propagating voltage amplitude. V0 plus is a whole bunch of mathematical formula. All right? So this is only to conclude up to now that indeed, once we provide you the operational frequency, once we provide you the transmission line parameters, right? You know gamma, alpha plus J beta. You know the effective wavelength. And once we provide you the connected load impedance, basically you know everything. You know the voltage and current as a function of space on the transmission line everywhere. Okay, so everything can be solved. So you understand what's going on the transmission. So that's a quick summary to the mathematical derivation. And starting from the next minute, we are going to understand about transmission line with certain load in more details. I would say these are more specific cases, right? So up to now, we have derived all the general solution forms. And then we're going to look into specific. We spent so many hours. So we now know everything on the transmission line. Okay, so special cases. Again, over the weekend, I have to thank one of the students who wrote me an email asking 2 questions. So the first question was, we talked about lossless transmission lines, right? We made the assumption the transmission line is lossless, and then we defined the reflection coefficient, right? The reflecting coefficient. So his question was, does the definition of the reflection coefficient still holds, even though the transmission line is lossy? So the answer is yes, it will hold, because the reflection coefficient is the reflection at the low point, okay? So basically, if you have loss, the reflection coefficient definition still holds. It's only through the teaching we want to make everything simplified, okay? So having the loss or not is not really going to affect the derivation results, but it's going to make things more complicated, okay? So even though we have loss, all you have to do is, well, you include all of the, right, everything. You just add the loss term back, and you will see how massive it becomes. When you add the loss term back, all these derivations are slightly more complicated, but the most complication will be in the standing wave ratio. Because the standing wave ratio, the amplitude, once you include loss, it's very hard to write out the analytical equation. Okay? So, simple answer, it will hold. Everything I'm teaching now are still valid, even though we have loss. But usually, as professors are really lazy, we just say that loss is not there. Okay? And the second question is a very nice one. So he was also focusing on the reflection coefficient and the standing wave. So he was trying to relate to the rope wave that everybody here learned during junior high school, right? So if you have a rope attached to the end of a wall and you try to just do this, and you will create a standing wave. This is exactly identical. Okay, exactly identical. It's just a different wave. But having the standing wave means you have an input wave and you have a partially reflected wave. So you will have standing. Okay, so I have to thank the student for writing the email, asking the question over the weekend. So let's move on. So the special cases of lossless transmission lines. So now the special cases are more pronounced if we don't have loss. But again, if you have loss, if you want to include loss, just include it. It doesn't really make a lot of difference. So the first case we're going to look into is short-circuited. Okay, the second one is open-circuited, half-wave, quarter-wave, and matched. So I am trying to divide or classify the special cases into 5 different types. The first one is shorted. Okay, shorted means I have a long transmission line, and at the end, they are connected directly by another wire. The formal definition of shorting, shoto, right? Shoto. Shoto is Japanese or Taiwanese, I don't know. Short, okay? You just short it. So by shorting your transmission line, what are you trying to enforce? If you're really good at math, by shorting the transmission line, you are forcing the boundary condition. Voltage at Z equals 0 or D equals 0 is forced to be 0, right? By short, by definition, you cannot have voltage. But once your voltage is 0, what happens to your current? Think about it. As I unfold, think about it. By short, definition is voltage has to be 0 at that point. But what happens to the current? Right? This is something we know already. We know how to write the total voltage phasor as a function of space, and we also know how to write it down for the current phasor as well. By short, gamma V is now -1, right? Because your load impedance, ZL, is 0. So your reflection coefficient is -1. So that's why here, for the voltage, you have a -1. -1 times exponential negative J beta B. So this is going to give you some kind of voltage phasor, total voltage phasor as a function space. Now for sine beta d, d equals to 0, sine is 0. So indeed, when you short circuit your transmission line, at the short circuit position, d equals to 0, you cannot have voltage. Right? So voltage has to be 0. What happens to the current? Think about it. Usually, our understanding is, well, if a position is not having voltage, your current is voltage divided by impedance, right? So 0 divided by something is still 0. But look at the expression. Because gamma V, the reflection coefficient, is now -1, so the current total phasor is not having a plus. So exponential j beta d plus its complex conjugate is now having cosine term, cosine beta d. When d equals to 0, cosine of 0 equals to 1. So this means even though at the termination you short circuit the transmission line, you don't have allowed voltage, it will be 0 forever. That point cannot have a voltage value other than 0. But the current is actually picking up its maximum value. So this is something you have to understand. This is very different, right? Because usually you think, well, voltage divided by impedance gives you current. But in this case, 0 divided by something gives you maximum. Is it really possible? It's possible because we're looking at the result of standing waves. Okay. If I don't know whether I want to go into the details, but gamma V equals -1. Think about it. Gamma V equals -1. So the total voltage is your input voltage 1 minus 1, right? At D equals to 0. So 1 minus 1. Ideally, you want to add the two. But the reflected wave in terms of voltage is -1, so it cancels out. So if you want to look into the definition of gamma V, why am I always adding this V? No one asked me about this question. The reflection coefficient can be defined as V0 negative to V0 plus. Okay. So by this, reflection coefficient is referenced to the voltage. You can also try to define the reflection coefficient in terms of the current amplitude. You can also have this, I0 minus I0 plus. That's also possible. Go back home, you're already at home. Go back after the class and try to derive everything using the definition of gamma I as defined by the reflected current amplitude to the input current amplitude. You will see that in this case, when the short-circuited transmission line, your gamma V is -1, but gamma I is 1. So you will have the maximum value of current at the short-circuited termination. Right? But today, I am going to focus on something more deeper. Right? What I want to tell you is, by looking at the special cases, we can have a more deeper understanding to what we derive the wave impedance in general, right? So if we divide the voltage phasor, total voltage phasor, by the total current phasor, this is what we have. So when we short circuit the transmission line, and I can walk back freely for a distance of L or D, okay, my wave impedance in this case is purely imaginary. And it oscillates as a function of tangent beta L. So this is the moment where you have to think. Tangent. Beta is a constant, 2 pi divided by lambda, but L is a free parameter, right? So I can terminate my transmission line and walk for any length and look back and say that's my effective wave impedance. So L is a free variable. So now you have to think and look at this equation and tell me, what do you see? You have to come up with some kind of conclusive statements. That's a process where you are teaching yourselves, so you will remember forever. What I can see is, well, let's go back to the blackboard. The first thing I see is when I have short circuit, so I have purely imaginary impedance, right? And then it's a function of tangent beta L. So is there any limitation or boundary for tangent? Or let me write it in this way. Tangent beta L is smaller than 1 and greater than 1. Tangent is unbounded. Right? Tangent oscillates from negative infinity to positive infinity. And then the entire thing is purely imaginary. What does that mean? It means when you short circuit a transmission line, and well, the transmission line is lossless, okay? So that means the effective wave impedance will change its value as you change the transmission line length, okay? So this is like I short circuit the transmission line and I walk for a certain distance and look back. Oh, that effective impedance is purely imaginary, but its value can change from negative infinity all the way to positive infinity. Okay? But what's the physical meaning? What's the physical meaning when you have a purely imaginary impedance? Anyone wishing to answer? No? The TA wants to answer. If you have a purely imaginary impedance, it means effectively that short-circuited transmission line can function as an inductor or a capacitor. Right? This 2 wires is equivalent to an inductor or a capacitor, and it's variable. You are free to change it just by cutting the right length. Okay? So let's come back to this figure. So if you short circuit the transmission line at the shorted position and you walk back a certain way for a certain distance within a quarter wavelength, it will be positive, right? Tangent is reaching infinity at pi over 2, 90 degrees. So that's 1/4 of wavelength. Within that distance, it will always be positive. And a positive imaginary number as an impedance means within this distance, that short-circuited transmission line is inductive. So you can fabricate an inductor of any value, 0 to infinity, just by using a segment of shorted transmission line. Okay? Now, once your distance passes lambda divided by 4 and 2 lambda divided by 2, then you have the negative cycle of tangent. And now you have a purely imaginary negative impedance. Negative impedance implies you have a capacitor. So this is the freedom of transmission line. So the reason why I derived all this wave impedance is really to show you that the transmission line itself, if you don't want to use it to deliver power, itself is very useful. If you don't have an inductor at hand or you don't have a capacitor at hand, all you have to do is cut a piece of transmission line and just short it, okay? And then you calculate the right length, it will function as a capacitor or an inductor. All right, so it's periodic. So it will be inductive, capacitive, inductive, capacitive. It's periodic. Look at the 3 figures very carefully and tell me, what do you observe? There is another comment. So you have to learn the right process of learning. The most efficient way to learn is you teach yourself, okay? Not through my mouth. What do you see? If you're really good at math, I mean, look at sine beta d, cosine beta d. If you're not very good at math, I'm showing you the plots. Voltage, total voltage as a function of distance is having a periodicity of lambda, right? Voltage, current, they're having a periodicity of lambda. But the wave impedance has a much shorter periodicity, right? So this divided by this is giving you a periodicity of lambda divided by 2. So this means for wave impedance, whichever value you have at certain distance, it will repeat itself. You will have the same value by another separation of lambda divided by 2. For each lambda divided by 2 distance, you will recover the same value. Okay? So this is very useful for the later contents we are going to use today. But what does that mean? For students, if you want to earn points, this is a trick all the professors like to do on your homework, on your examination. You don't have the quiz, bless you. It's periodic, right? So whenever we ask you certain question, oh, what is the impedance value or the effective inductance here? If you want to write the full answer, you have to remember the answer is having infinite choices, right? It repeats at itself after lambda divided by 2. Okay? So that's the case with short-circuited. Next case, for, I went through this already, right? If tangent beta is positive, you have effective inductor. If it's negative, then you have effectively a capacitor. Open-circuited. Open is being lazy. You have a transmission line and you do nothing. Doing nothing is open, all right? So the formal definition for open is your voltage is now having the maximum value it can be. But the current, when you have an open, you cannot have current, right? So current has to be 0. So let's check. Just by changing gamma V to 1, positive 1, and your current total phasor takes on the form of sine beta d. So for d equals to 0, sine is 0. So indeed, yes, at the open end, you cannot have current, but your voltage is having the maximum. Again, remember, this is the fact due to that we're studying standing waves. Okay. So without showing you the last figure, can you guess? If I divide this one by this one, I have my wave impedance for the open case. What does it look like? Do you have to start everything over again, or try to just slightly change the summary we derived on the blackboard? That's what short-circuited, but now it's opened. Is the resulting wave impedance unbounded or bounded? What is happening to its periodicity? So think about it. So all you have to do is divide this equation by this equation, and you have cotangent. It's still purely imaginary, but you have a negative sign, right? So you have a negative j, imaginary, negative cotangent. Cotangent is only the inverse of tangent. So basically, in this case, you have a piece of transmission line, you leave it open. Effectively, your wave impedance as a function of distance is still purely imaginary. So you can also use this case to fabricate inductors or capacitors. But the fact you have a change in sign for your gamma V reflecting coefficient. So now, between the distance of 0 to lambda divided by 4, you have a purely capacitive reaction, and then it's inductive, capacitive, inductive. So the only change is, from the short-circuited case, you have inductive, but now you have capacitive. Nothing else changes. Okay? The periodicity is still lambda divided by 2. Okay? Now, we are going to look into something magical. Well, this is something I like. When you have a load, okay? You connect the load to the transmission line, and you walk for a particular distance towards the generator, and you look back. And that magical distance is lambda divided by 2. Okay? So let's use this equation. Okay? This is what we derive for the wave impedance. And now let's make L equals 2 lambda divided by 2. You still remember beta equals 2 pi divided by lambda. And now you make L equals lambda divided by 2. So tangent beta L is tangent pi. Right? Tangent pi. Tangent is sine divided by cosine. Sine pi is 0. So basically, in this case, you don't have to care about these two terms. Right? You don't care about these two terms. So your effective input impedance is Z0 multiplied by the normalized load. Normalized load is ZL divided by Z0. So basically they cancel. So what does that tell you? For whatever load you connect to the transmission line, whatever, okay? And then you just walk for a distance of lambda divided by 2. You look back, including the transmission line and the load, at this particular magical distance, the wave impedance is equal to the load impedance. It's magical, right? So this is telling you over a very long transmission line, you can say a lot of the length is invisible, right? When you choose the position right. So what happens when you are walking for an integer multiple of lambda divided by 2? It's the same because tangent is the periodical function. So that means for the transmission line, no matter how long it is, and no matter what load impedance you connect to it, there are a lot of magical positions, discrete magical positions. Once you stand on the magical position, you look to the direction of the load. The transmission line plus the load gives you an equivalent wave impedance equals to the load. Okay, so I mean, in physics, in real life, this is like what I'm doing to you now. You're sitting at your home, maybe 1 kilometer away from me, but you can hear my voice, right? Although the camera is only 2 meters away from me, but you can hear my voice. So this is like engineers can cheat, right? Even though the load is 1,000 kilometers away from me, I can treat you as just 1 meter in front of me, when your magical position is determined. You can do that. You have the freedom to do it. Okay? You can effectively make the transmission line much shorter and do all the calculations there. Okay? So in your numerical calculations, even though you have 1,000 kilometers to be solved, you can make it short to be maybe 50 centimeters. Okay? So this is really calculation saving strategy once you know it. So this happens when your length is integer multiple of lambda divided by 2. So this is called the half wavelength line. Okay? Half the wavelength. Quarter wavelength. This is something deeper. Okay? So this is saying that I have a transmission line of certain characteristic impedance, and I have a load, and somehow I know that the load impedance is not equal to the characteristic impedance. But is there any possibility I have a second transmission line so that I can connect the second transmission line to my load, and I choose the right length so that together the second piece of transmission line and the load will match to the characteristic impedance of my first transmission line. Okay? Again, we're using this formula. This is what I derived it for you today. So now the length is lambda divided by 4, and as we know, wave impedance is periodic with a periodicity of lambda divided by 2, right? So you will have a lot of answers. So once your length is lambda divided by 4 and the integer multiple of half wavelength, all the results will be identical. So tangent of this value, tangent pi over 2, you have infinity. Okay. So in this case, we can ignore this 2. the real parts, right? Because tangent is now super big. So we remove this two. So in this case, the second transmission line with a length of quarter wavelength plus the load together will give you an impedance of the second characteristic impedance squared divided by the load impedance. So somehow I can say this value is equal to Z01, right? So this is one way to accomplish the so-called impedance matching, which will become our focus for the next class. But now I'm already offering you one way to accomplish, to match the load impedance to the characteristic impedance of the transmission line if you have a second set of transmission line with the right characteristic impedance. Okay? All you have to do is write down this is equal to Z01, and you find out the proper Z02. If you happen to have that set of transmission line, then you can perform impedance matching. Impedance matching means you have maximum amount of power delivered to the load because there's no reflection. Okay. So I talked about 5 special cases: short, open. They both give you purely imaginary impedance with unbounded value. So these two are especially useful for providing effective inductor or capacitors. Half wavelength is a magical distance where the load reappears at these locations. Quarter wavelength could provide you a potential way to accomplish impedance matching. Of course, in the end, our goal is to really have matched lines. We want to perform impedance matching so that we can eliminate reflection. So all the powers can be delivered. Okay? Once you don't have reflection, the maximum power can be delivered in the positive direction. All right, so let's take a 10 minutes recess. So next class, for the entire next class, I'm only going to talk about one thing: impedance matching. A lot of mathematical derivations, so be ready. durations on the blackboard. Not a lot, only 3 lines, but if you have time, you can just write down for now. So as I said, the focus for the next 15 minutes is only on one thing: reaching impedance matching. Because when we have a matched line, we can deliver the maximum amount of power to the load. Okay? So there are 2 ways to do it. I won't go into the details for now. I will talk about the general consideration. Right. So usually, we have a transmission line, we have a generator, and we have the load. It will be very difficult for the load to really match to the transmission line. It's in our dream, but it's really not possible always. Okay? So let's take a look at the load impedance. A load impedance can be separated into 2 parts. The first one is the real part, the resistor. Second part is the imaginary part, right? Capacitors or inductors. So in any case, the impedance is a complex number. It will have its real part and its imaginary part. And since the very reason we want to assume the transmission line is lossless is the characteristic impedance in this case will be purely real. Okay? So think about it. We have a load. It's a general load. The resistor value can be anything. Imaginary value can be anything. And now our goal, our target, is to say that the load impedance will be matched to this. Z0 for a lossless transmission line is purely real. So then you have to ask yourself, is it possible? Impedance matching means the load impedance ZL is equal to Z0. But Z0 is a purely real number. So there's no way, in general, to reach impedance matching. Okay? So we can only hope for by hope. Let's do this. Okay, hope that somehow, okay, through the knowledge, we have RL plus JXL and somehow transformed over a distance d, right? You still remember we defined the wave impedance. So which means I start with a load, I know my load, I walk for a certain distance, I look into the right, that's my input impedance. So the input impedance, we know, can vary as a function of distance, right? But usually, the wave impedance is also a complex number. So now, after I walk for a certain distance, I look at the input impedance. It's RS plus JXS. Or let me say D. What am I using? D. I'm using D to denote the resistor value and the imaginary value, reactance value, are both a function of distance. Okay? So somehow I converted the problem to this one. Initially, I have my load, which is a fixed value in terms of the real part and imaginary part. But something I learned in the past 15 minutes, I know that if I walk on the transmission line, and that transmission line segment plus the load will convert into a new impedance. And that new impedance is changeable, right? So even though in the case RL is not equal to Z0, remember again, this is real for a lossless line, right? So even in the case, my starting point is my load resistor value is not equal to the characteristic impedance of my transmission line. I have some kind of hope by walking for a certain distance on the transmission line, and I look at the transmission line together with my load, somehow, potentially, RD is equal to 0, Z0, right? Then I have a very good starting point to achieve impedance matching. So think about it. Do you understand the philosophy up to now? The load itself is not matched to the transmission line. But what I can do is, by walking for a certain distance, then I'm using the effective ZD, right? I'm combining the load and the segment of the transmission line to function as an effective impedance. And then I know I can change the values in the real part and the imaginary part. So let me write explicitly for you. These are both functions of distance. So it's changeable, tunable. So you might be able to find the right distance where the real part is magically equal to the characteristic impedance. So at least the real part is matched. But then in this case, XD, what happens to XD? XD is the imaginary part to your wave impedance. We want to kill it, right? Why do you want to kill it? Because by impedance matching for a lossless transmission line, the characteristic impedance is what to be matched. It only has a real part, so we need to eliminate the imaginary part of the wave impedance, right? So this is the overall goal. Our overall goal is to find the right position on the transmission line, including the load impedance, and at that position, the real part of the wave impedance is matched to the characteristic impedance of the transmission line, and somehow you cannot just pray for this condition to happen. Okay, this is something artificially we have to manipulate. We have to do something else. Okay? So are we clear up to now? Then it's the next PowerPoint page. Okay? So this is what we're going to do. This is what we're going to do. I'll explain what we are going to do, and then again, and then go to the blackboard. All right. Think about how to kill or eliminate, if you don't like the wording kill, how to eliminate or remove the imaginary part of the wave impedance. We have a load. We have a transmission line with the right distance, right? The way we want to perform impedance matching is we don't want to cut anything. Okay, at least we don't want to cut the transmission line. Assume the transmission line is already connected to the load. Wouldn't it be better if the impedance matching can be performed in a non-destructive way, 非破坏性, we don't harm anything. So at this distance, I already know that the real part of the wave impedance is matched to the characteristic impedance of my transmission line. All I have to do is kill the imaginary part. How to kill the imaginary part? Okay. What do I mean by killing the imaginary part? If the imaginary part of the wave impedance is positive, it means you are having an effective inductor, right? So you have a positive imaginary value. And then we can connect what? The capacitor in parallel to it, right? To make the imaginary part going to zero. Why? Capacitor will give you a negative imaginary part in terms of its impedance. Okay? So we're working everything in parallel, because working in parallel, we don't have to cut anything. We don't need to cut the transmission line. And therefore, it's a non-destructive way. Right? Since we're working everything in parallel, we want to convert everything into the admittance. Admittance. Okay. So now I'm showing you the input, the load admittance is the inverse of the load impedance. Admittance is just divided by 1, but 1 over DL. Okay? So everything is now working in parallel. So let's go to the blackboard. So when everything is working in parallel, 1 over Z total is 1 over Z0 plus right? Everything. I'm trying to explain why I want to use admittance, because when you have something working in parallel, you have to add the reverse, right? Reverse adding reverse equals reverse. This is very tedious, so why not just use admittance? Y0 plus YD, right? Admittance, you add them directly. Okay, so now what is my general philosophy? I know somehow, right? Starting with my load admittance, I walk for a certain distance, I will arrive at my effective wave admittance, YD. Okay. YD is still complex. It still has a real part and imaginary part. But somehow I can kill the imaginary part by shunting. Shunting means connecting something in parallel, shunting, to remove the imaginary part. Okay? So, YD. The wave admittance is also having the real part and imaginary part. Okay? So my goal is, oh, this is tedious. Okay. How should I write it? Yes. So let me remove this one. what I'm trying to do is YD is the admittance of the node plus a segment of transmission line. Then I want to connect something in parallel, which is purely imaginary. So this Y total would be GD plus J, BD plus BS. Okay, clear? Because I'm connecting something in parallel, which is purely imaginary, so I only add the imaginary parts together. So GD is the inverse of Z0, and BS is equal to, I have a special way of writing it. Negative BS would be BB. Okay. So this is my overall target. By connecting a purely imaginary component, maybe a capacitor or an inductor, at the distance of d, what I'm trying to do is I want to kill this. Right? I want to kill that. So I only have the real part remaining, and at that distance, the real part of the impedance is Z0, matching to the transmission. All right, so let's go. Where should I start? I'm still starting from what we learned last class, the wave impedance. The wave impedance is defined by the total voltage phasor divided by the total current phasor. Okay? So now, remember, the reflection coefficient is usually itself a complex number, so I'm writing it as an amplitude with a phase. Okay? For simplicity, I am going to call this theta gamma, which is the angle of the reflection coefficient, minus 2 beta d as theta prime. This is for simplicity. So now we have the simplified formula for ZD, the wave impedance. I can invert it. I invert it, it becomes the wave admittance. Okay? Admittance. It's just flipped. What I'm trying to do now is to rationalize it. 有理化, rationalize, right? I have 1 plus gamma E, absolute value, exponential j theta prime. I want to rationalize it, so I don't have this exponential terms anymore. I multiply the same thing on top and bottom. This is called rationalize. After all the manipulation, you will have the picture file. The TA took the picture already. Okay, so you will have the real part and the imaginary part. So this is the front part is my GD. The second part multiplied by this is my BD. Okay. So take a few moments and try to jot down if you want. I will rewrite this for you. Which color am I using? All right, so this is summarized here for you. I merely copied what we had on the blackboard. So now I'm isolating the terms. So the real part of the wave admittance is this form, and the imaginary part, okay, of the wave admittance is written in this form. So now we have to solve. How to solve it? The easier one, now we have two equations, right? We have two equations. What things are we trying to solve? Eventually, here, the characteristic impedance is given. So this is known. Reflection coefficient, known. The only thing unknown is theta prime. Okay? So actually, with only one unknown, there's no need for two equations, right? So we can actually know theta prime just from this single equation. 1 over z0 equals 1 over z0 multiplied by this. This is 1. Okay. So this converts into 1 plus gamma v squared plus 2v cosine theta prime is equal to 1 minus v squared. So you kill the 1. So this is 2 times gamma v. I can remove gamma v. So I use a different color. From this very simple equation, it immediately tells us the only remaining parameter to be solved is so easy. Once you know your voltage reflection coefficient, you take its absolute value, take its negative, and you have theta. Straightforward, meaning impedance matching is not very difficult. Once you know how unwell it is matched or how big it is mismatched, you know how to fix it. Okay. But at this point, straight on, let me ask you this question. Is that cosine solution a valid solution? Cosine theta prime equals to the negative of an absolute value. So cosine is negative. Is it valid? Cosine values usually are smaller than 1, greater than -1. So is it still valid? So this is a point to your understanding. How big is gamma v swinging? Gamma v is, again, limited to below 1 and above -1, right? So this is valid. So this is okay, because this absolute value is bounded by -1 and 1. That's basically this absolute value is above 0 and 1, so it's okay. And then you have to think, this is the critical point. How many choices do you have to accomplish impedance matching? Cosine. This is the absolute value, so cosine theta prime must be negative. So cosine takes on positive values in the first and fourth quadrants. and positive in second and third quadrants. So this means for every impedance matching problem, you always have two solutions. So you always have you will have two choices of theta primes. For each theta prime, do you still remember how theta prime is defined? No. Theta prime is defined by the reflection coefficient angle minus 2 beta d. So it means for each theta prime derived, you have a corresponding magical distance. So theta prime comes in with a pair. Try to pair up with the right distance. Okay? So remember, whenever professors are asking you to perform impedance matching, it's trying to trick you. There are two potential choices. At location 1, you have to connect certain imaginary part, right? And there's another location where you can connect another type of imaginary component. Okay, remember, two choices, two distances. Okay, so under this condition, since cosine theta prime is negative absolute value of gamma b, this can be simplified, right? So let's try to simplify this. So this is negative 1 z0 times 2 b sine prime 1 minus gamma b. Do you see what I'm trying to do? So this is negative gamma b, right? Is that right or wrong? I think I wrote it wrong. Square is here. Okay. So this thing is becoming negative 2 gamma v absolute value squared, right? So you have 1 minus only 1 gamma v absolute value squared. Okay, so are we clear up to now? I have maybe 20 minutes more, so I want to show you how to calculate with one example. Okay. So this is on your slide 27. I am trying to give you a real example. So you know your operational frequency is 100 megahertz. You have a 50 ohm lossless transmission line, which you want to perform impedance matching to a load where the real part is 25, right? 25 is not equal to 50. You know you have to perform some kind of impedance matching. So the load is having its real part, imaginary part. Fine, let's try to work. Take a picture. Okay. All right. First step, calculate your reflection coefficient correctly. So step 1, gamma v is always calculate your reflection coefficient correctly. Once you know the reflection coefficient, right? I'm writing in a way that the reflection coefficient is having its amplitude and its phase. Okay. So once we know the reflection coefficient, we already know cosine theta prime. Right? So the second step is remember forever, you have two potential choices. So now cosine theta prime is now negative 0.62. Okay, let me just write it out for this problem. So when you type into the calculator, it should return one single value, but you know if your answer is in the second quadrant, you need to calculate the result in the third quadrant. Okay. So this is and the beautiful thing about cosine function is once you know the angle, the other one is the negative to it, right? So once you have this value, just add the negative sign. So you have the other angle. So this is step number 2. Try to clearly define that you have two potential theta prime angles. And then you can calculate the corresponding two distances, D1 and D2. Just erase the prime here. Okay? You don't really need a prime. So, third step, D1 and D2. Okay, so let me write down this for you. Let me derive for you. So theta prime is defined as theta gamma minus 2 beta d, which is theta gamma minus 4 pi divided by lambda times d. Okay? So d is theta gamma minus theta prime 4 pi times lambda. Okay? This is from the definition of theta prime. So d1 is, in this case, wait. Yeah, that's right. Lambda divided by 4 pi. This is somewhere you have to pay attention to. Usually from the calculators, we have the angles in degrees. When we look at lambda divided by 4 pi, this is converting the angles into radian. Okay? So this is negative . We need to convert the angles in degrees into radians. How to do that? (180 degrees is corresponding to a pi phase in radian, right? So we convert from degree to radian by this. So this is giving you the D1. The D1 is 0.0631. Okay. So if we want to accomplish impedance matching at the distance of this from the load, we have to connect something to be defined. The second one, lambda 4 pi. This is another trick. Okay. Negative 82.9 degrees minus 128.3 degrees times pi divided by 180 degrees is pay special attention. Negative. We're done, right? What does a negative D stand for? A negative D stands for we have to perform impedance matching somewhere to the right of the load. It's impossible. So after all these efforts, we end up with one of the solutions to be impossible. Smart students like you, do you still remember what I said in the last class? Wave impedance and therefore wave admittance are periodic. What is the periodicity? Lambda divided by 2. So remember. This means you have lots and lots of choices in terms of the distance where you shunt some component, right? So in this case, let's make n equals to 1, and then I'm safe. Okay, here n equals to 1. So I can almost guarantee you in your calculations, you will encounter one of the distance to be negative value. So you have to add 0.5 lambda to it, and then you're secure. Okay. So now, third step, we know the theta, we know where to perform the parallel connection. Now the point is what to be connected in parallel to. Okay, so number 4. I know my theta prime value, right? And then I can just plug it to here. And I know my BS value, right? So theta 1 prime has a BS1 value, BS2 value. So these are in the unit of Siemens. So the beauty again is once you know one answer, the other one is just the opposite sign. Number 5, I want to really convert it, okay? What I really care about, B is the reactance, the imaginary part of the admittance. I don't like it. I'm going to flip it back into impedance, the imaginary part of impedance. So X, S1 is the inverse, and then the negative sign. I'll come to the sign part later. Okay, so let's take about the value first. This 31.62 ohm is nothing more than inverse of this value in Siemens. Okay, inverse. Okay. So why do I need to flip the sign from a negative B value into a positive X value? When you have J omega L, right? This is, for example, in the B domain, you inverse it. So you have J omega L inverted. Having this J, you have to multiply the J and J. J squared becomes negative. Okay? So remember, these are the particular tricks in dealing with complex numbers. The imaginary part would flip sign when you invert it. Okay? So a negative value of b would give you a positive value of x. So by looking at this, for distance number 1, you need to connect something in parallel, and you have a positive value. So that means ZL D1, you are connecting an inductor. Yes, question?
有人问为什么 D2 不能是负的？
Oh, because you have a load, right? You have a load. For example, this is your cell phone. This is your cell phone connected to the plug. Can you perform the impedance matching by doing something to your cell phone? It's impossible. You don't want to destroy your cell phone. So D is defined to be 0 from here and going positive in that direction. So if you have a negative D, it means you're doing something impedance matching to the back of your load, which is not allowed, right? You have to take out open your cell phone and do something. If you're very confident, you can do it, okay? But usually D should not be negative. D negative means it's something here. Load is our termination, right? So we can do all the tricks before the load, somewhere between the source and the load. This is free, but somewhere behind the load is not accessible. Is that clear? Any more questions? I think the student can hear me, I think, right? I'm trying to answer. All right, so let's come back. So this. So omega L equals to 31.62 ohm, and omega C equals to 31.62 ohm, right? So the first choice, add distance of D1, of course, plus integer multiple of lambda divided by 2, I can make a parallel connection of an inductor. For the second one, this is my load. D2, I can make a parallel connection of a capacitor because it's negative, right? So I know that omega times L equals to that, 1 over omega C equals to that, okay? So you might be surprised. After all this messy derivation with very bad looking numbers, yeah, beautiful. Beautiful results. It's almost impossible. So somewhere the textbook author really tried to do excellent work. Okay. So this is telling you at 0.063 lambda plus integer multiple of lambda divided by 2, you can connect an inductor of 50 nanohenry. Nano means times 10 to the minus 9. Pico means 10 to the minus 12. Okay? So you have two choices. Here, you can shunt an inductor, or at the D2 location, you can shunt the capacitor. And then you can enjoy impedance matched transmission. You have the maximum power delivered to your load. Okay? This takes work and dedication and care. What I would say is care, because I want to emphasize again, for all the impedance matching problem, you have to remember there are two potential choices, right? So one of the choice would be making parallel connection using an inductor. So you have to choose the position right. If you want to perform impedance matching using a capacitor, you will need to find the right location, okay? So you always have two choices, inductor, capacitor. So I still have 1 minute. For the very last page, I'm not going into the details, but it will appear in your homework, and I promise you it will show up in your examination. If you still remember, if you cannot buy the inductor or capacitor, what can you do? If you still have a piece of that transmission line, like what I taught you, for short-circuited or open transmission line, for changing the length, you can change it into an effective capacitor or effectively an inductor, right? So if you cannot buy the inductor or capacitor, you can just use a piece of right length transmission line to accomplish impedance matching. Okay. So with that, I'm closing the topic of transmission line. So on Wednesday, we are going to march into vector analysis, which is an easier topic for you. But somehow, for all the transmission line parameters like capacitance, inductance, resistance, we don't know how to derive up to now. So for the later part of the semester, we are going to learn how to properly formulate the transmission line parameters, right? R prime, G prime, C prime, L prime, right? So we start with a very clear guided topic, direction, and we will finish everything for the rest of the semester. All right, so do we have questions? I really need to thank students for asking the question because it takes courage. Any question? If not, I'll see you on Wednesday. Thank you.